So today we're going to consider the cardiac cycle, which refers to the pressure changes occurring in the various chambers of the heart whilst the heart is beating. And the best way for us to examine this is by use of a graph. So in this case, the horizontal axis is time and the vertical axis is pressure. The units don't really matter, but the normal unit of measurement for pressure in the cardiovascular system is millimeters of mercury. So the first line that we're going to draw on here is going to be the pressure in the left atrium. So for the rest of this tutorial we're just going to be thinking about the left side of the heart. So this is the waveform showing pressure changes in the left atrium. And what we can see is that there are a number of phases in this waveform. So initially, up to this orange dashed line, what we have got is passive filling of the left atrium. So this is atrial filling, and I'm going to abbreviate that to AF. So this is the passive filling of the left atrium. You'll notice that during passive atrial filling, the pressure doesn't really change, and this is because of two main factors. First, most of the blood that's entering the atrium during this phase is draining directly down into the left ventricle through the mitral valve, and secondly, the atria are quite distensible, so they can expand to a bigger volume without increasing the tension in their walls. Both of those factors maintain that pressure at about the same level. Now, the next phase, here, we can see that there is a rise in the pressure within the left atrium. And this spike in pressure of the left atrium is caused by atrial contraction. So here the atrium contracts and forces blood down into the ventricle, and because it contracts and squeezes the blood, the pressure in the atrium increases. So this is the phase of atrial contraction. Now, following atrial contraction, as you know, the ventricles contract. So this third phase is ventricular contraction. And what you can see is that the pressure within the left atrium gradually increases during ventricular contraction. The reason for this is mainly because when the ventricle contracts, in this case the left ventricle, the mitral valve closes, meaning that we no longer have a pathway for blood to passively flow from the left atrium to the left ventricle. So because the mitral valve has closed, the left atrium will fill up and the pressure will gradually increase. But you'll notice at the end of the phase that we've previously described, the pressure in the left atrium suddenly drops, and this is because the mitral valve opens after the ventricles have emptied and atrial filling continues. So here atrial filling is continuing, and that explains that little drop in pressure in the left atrium. So now let's examine the waveform showing pressure changes in the left ventricle. So you can see that during passive atrial filling, the pressure in the left ventricle doesn't rise appreciably, and this is because, once again, the left ventricle can distend and blood is just gradually pouring into the left ventricle, but not under any kind of motive force. When the atria contract during atrial contraction, you can see a little spike in the pressure in the left ventricle, just like we saw in the pressure in the left atrium. And this is because blood is being squirted, ejected from the left atrium into the left ventricle under pressure. You can see that when the left ventricle contracts during ventricular contraction, there's a big spike in the pressure in the left ventricle, which you would expect because it's working very hard to force the blood out. And then the pressure drops below the pressure in the left atrium, and so blood is then able to go from the left atrium to the left ventricle again to fill the ventricles up. And that's an important general rule, that blood will travel in the direction of its pressure gradient. So it'll go from high pressure to low pressure. Now, before we continue, let's just write down the colours that we're using for these different curves. So the left ventricular pressure we've used red for, and the left atrial pressure we've used blue for. So now let's add on the aortic pressure. So let's put the pressure in the aorta onto the graph. And for the aortic pressure, we'll use green. So here are the pressure changes in the aorta. So when we look at pressure changes in the aorta, we can see that during atrial filling, in the phase of atrial contraction, the pressure in the aorta is gradually diminishing until we reach the point where the pressure in the left ventricle exceeds the pressure in the aorta, and then blood will flow into the aorta and its pressure will increase. After the ventricles have finished contracting, then the pressure in the aorta continues to decay down. And I think it's worth pointing out to you at this point that when you hear someone's blood pressure being quoted, the two numbers that we get, the systolic and the diastolic blood pressures, are actually between these two black dashed lines. So, you might hear someone having a blood pressure of 120/80. Systolic pressure is the maximum pressure in the aorta following ventricular contraction, and the diastolic pressure is the lowest pressure found in the aorta before blood enters it following ventricular contraction. Now, I want to point out a few important places on this graph which you need to be aware of. And these are mainly the intersections between the different curves. So let's start off by considering this point here. So you'll notice that this is the point at which the pressure in the left ventricle exceeds the pressure in the left atrium. And this point that I've just circled is the point at which the mitral valve closes, because the pressure in the left ventricle is higher than the pressure in the left atrium. This closes the valve. At the opposite end, at this point here, you'll notice that the change in pressures is the opposite, i.e. this is the point at which the pressure in the left atrium exceeds the pressure in the left ventricle. And so this is the point at which the mitral valve opens, allowing the ventricles to fill from the atria. If we consider the relationship between the pressure in the aorta and the left ventricle, we've got this point here, and this is the point at which the pressure in the left ventricle exceeds the pressure in the aorta. So that's where the aortic valve opens and blood enters the aorta from the left ventricle. And on the opposite side, we've got this point here, which is the point at which the pressure in the aorta exceeds the pressure in the left ventricle, and that's where the aortic valve closes. Now, I'd also like to point out this little blip here in the pressure trace for the aorta. And this is a thing called the dicrotic notch. And what it represents is an increase in pressure in the aorta due to elastic recoil in the wall of the aorta itself. So, as the left ventricle is forcing blood into the aorta, energy is stored in the aorta's elastic wall, which is then returned back to the blood and helps to maintain the blood pressure at a slightly higher level. And that little notch is created by that elastic recoil of the aorta. So finally, for completeness, let's put on the ECG trace, which is the electrical activity of the heart and have a look at how that correlates with the changes in pressure in the different chambers. So what we can see on this ECG trace, which is drawn on the same time scale as the rest of the graph, is three major phases. So this first phase here is called the P wave. So this is the P wave. And what the P wave represents is the passage of electrical activity through the atrial walls. So the P wave is going to be the electrical activity preceding atrial contraction, and you can see that if you look down to the bottom of the graph. P wave occurs just before the increase in pressure in the atria when they contract. This complex looking waveform here is called the QRS complex. So this is the QRS complex, and what the QRS complex represents is electrical activity passing down through the interventricular septum in the His-Purkinje fibres and then back up through the ventricular wall. So we'd expect the QRS complex to occur before we start seeing pressure changes in the ventricles, and that indeed is what we see. So the QRS complex correlates with ventricular depolarization, ventricular contraction. Finally, the final part of the waveform that we need to look at is this, which is called the T wave. And what the T wave represents is ventricular repolarization. So this is the ventricular muscle recovering after its contraction. So this is the muscle fibers, if you like, resetting their electrical potential so that they can then go on to contract again. So I hope that this brief tutorial was of some help. As always, please feel free to pass on some feedback through the website. Okay, thank you. Bye.